Okay, so just to recap, we talked about electricity being electrons. Then we talked about ions and how electricity can be part of an element and in the form of an ion, which is still just the flow of electricity. And so if you have an ionic solution, you can run a current through that solution. So the current is kind of half your kind of normal wire stuff. So like electrons going through the wires and then from the battery. But then it's also now going through a solution. And so that solution of ions completes the circuit. And we know that if we take a rod, two electrodes, we put them into a potato, because your potato is full of ions, you actually will notice you can have a little, you can power a little light bulb there. So you probably go onto YouTube and look at that. Google potato light bulb, potato powers light bulb or something like that. Anyway, then we talked about electric fields, and we know that from a point charge, a positive point charge, electric fields go outwards, and then a negative, the electric field goes inwards. The more lines you have on an electric field on the paper, the stronger the electric field. And so if you have a wide distance between lines, it's a slightly weaker field. We talked about the distance from an electric field from that point getting weaker as you go further away, a little bit like going away from the magnet. Now we're going to talk about the forces. And so we know that fields exert a force on each other. And so I did the point charges, but I wanted, because I don't want to run out of time, I want to draw sort of an example of how charges might behave. And so we could have a positive and a negative charge sphere. And we know that these opposites attract, and so they would go towards each other. Now, this negative doesn't mean that there's no positives in there. It just means that there's more electrons than protons. Okay, so we could draw them there, and this might only have sort of half the amount or something. Now, it's still going to be more positive than negative. Maybe there's more positive protons in the nucleuses. Now, they go towards each other, opposites attract. Okay. Now, while they're in here, you could think of this is actually static electricity. This is the beginning of now learning about static electricity, which is your electrons confined into, well, we've got static inside our bodies. If I have woolen, these woolen slippers on, okay, which are, if you study, they'll often rub a woolen jersey with a ruler to show, and it's you'll notice if you walk around with woolen slippers and then you touch, even if you go try and have a sip of water, you'll notice that because you now are positively charged, the electrons then jump from the water and they shock you because they want to neutralize you, because the electrons have jumped from your body into the wall. So that's kind of electricity. Finishing off, what happens? These guys touch eventually as they're attracted. And so what happens? Electrons would move from that one. And so until they were both had the same amount of electrons. Now, if this is, say, I'm going to suck numbers out of my head here, but let's say that this is negative 3.2 coulombs, then you'll notice that they're usually in units of 1.6. And this is plus 1.6. Because overall, if you add these two, this one is negative. It's more negative than this one is positive. What we have here is the charge gets shared between these two evenly. So if you add these two charges together, you would get negative 3.2. That would actually sorry, negative 3.2 plus 1.6 would you have a balance of 1.6. That would be shared out now between these, because charge, electricity always wants to kind of balance itself out. So it usually likes to go to the center of the earth. But if it's here in this situation and it's not connected to the earth, if it was connected to the earth, those electrons are going down because that's where they want to go. Electricity always wants to go to the center of the earth. We've got an iron core that just loves electrons. So they would then be sitting there going 0.8 negative, 0.8 negative. And now what's happened? They're both negative. And so what are they going to do? They're going to repel. And so suddenly you're going to notice these spheres will go away. And that's a very popular question when they give you these two spheres and they say, what happens? They attract, the electrons flow from negative to the positive. They then have an overall charge. Sometimes it could be positive. And if the overall charge is positive, that doesn't matter. They're still going to repel because they would then become like charges and repel. So you got 1 attracting, 2 touching, movement of electrons, 3 repelling, as they now have the same charge, overall charge. Unless they're neutral, very unlikely that it's going to be an overall charge of 0. But if they did have an overall charge of 0, they would just kind of sit there next to each other. Okay, so we know that static electricity moves. So static electricity, if you rub objects together, so you could have so we noticed that a balloon sticks to the wall. You rub a balloon. And this is all to do with what happens is the electrons go into one of the objects, and that object becomes overall positive or negative. And once something has an overall positive or negative, as soon as it attracts to something neutral, it's going to want to share its electrons or take electrons. You can think of electricity just wanting to go from negative to positive. The flow of electrons is always from negative to positive. And so if you have a lot of electrons here, they want to go to that positive place over there. Okay, so now, okay, let's go on to, because you mentioned wanting to do Ohm's law. So we're going to spend the last little part talking about Ohm's law. Oopsie. All right. Okay, so we're going to start with the most important equation in our electric circuits, VRI. So electric circuit. So whenever I think of Ohm's law, I start to think of, okay, we're getting to the electric circuit section. Ohm's law is quite an easy one. You just got to remember this equation, okay? Because this is voltage, this is resistance, and this is current. And so we could say that the voltage, V equals R, we'll make it in terms of I. Now, this just depends on how you guys get taught it. But the current in a circuit now, what happens to the current of the volts? Well, big volts, big current, right? Because they're both on the top. So the current is in a circuit is directly proportional directly proportional. Now, there's a much quicker way of writing this. That, right? That means directly proportional. This little backward swimming fish. So I could write that as just I is directly proportional to V. That is shorthand for this whole thing here. It's directly proportional to the voltage. And indirectly proportional to the resistance. Because as the resistance goes up, the current goes down. Why? Well, current is the flow of electrons. Okay, I normally start with that because we're running out of time, and I think you probably already know that. Current is the flow of electrons. So if I resist those electrons, so if I increase the resistance, less electrons can flow. So it's directly proportional to the voltage, because I like to think of voltage as the thing that's pushing the current. And so the more voltage, the more current. And then if the resistance is the thing that resists it, pushes it away, and so the more resistance, the less current. So it's voltage and indirectly proportional to the resistance.
Is that the same in both parallel and series?
Yeah, but it's something different to start when we start to. So this, by the way, shorthand for this, I directly proportional to 1 over R. That just means indirectly proportional because of the 1 on the top. Good. So the question of the current in a parallel and resistor is, parallel and series is important, because when you put a current in series anywhere on the circuit, the current is the same, because we think of current as like water, right? Water in a pipe, okay, but it's not, no one's drinking the water. It's sort of going around. We've got to think of it like that. The current is the same on one end as it is on the other, but when it goes into parallel, it splits. So you could also think of it as runners, right? So I could put some resistors here. Now, I don't know if this is going to answer your question, but if I was to draw the current, coming along here, oh, shit. What happens here is it splits, but I want to just say that at the circuit, the current's always the same because it just keeps going around. It's like runners in a marathon as well. And so they get here and then they're split up. So the idea of these, I'm going to draw them slightly thinner to show that sort of some go there, some go there. So our Ohm's law still rings true for this. However, our resistance is the key to solving this type of circuit, because your resistance is the thing that changes depending on whether you put it in parallel or in series. If I take, I should have really put 2 resistors. Let me stick another one here. If I put another one here, And if say all these resistors are just 1 ohm, just for simplicity's sake. Well, we know that if I added these two in series, they would be 2 ohms, wouldn't they? Because it's 1 plus 2. 1 plus 1 is 2. Right? Happy with that? These two in series. But what is this? What is the resistance of these two in parallel?
1 over, it would be 1 over R1 plus 1 over R2.
Good, yes. So it's 1 over 1 plus 1 over 1, which is 2, right? But it's not that, because it's 1 over R parallel. So don't make the mistake of thinking the answer is 2. We have to flip it. So 2 over 1, if you flip it, is a half. So these, yes, these combine to make a 0.5. So William Smith, the great physics and science, chemistry, maths, all of the stuff used to be on TV. He used to say, okay, take these resistors and then just write down somewhere so that you remember, and you can treat it as a half an ohm resistor. So you can treat these two resistors as 1/2 ohm resistor in your calculations, which makes things a lot simpler. So your voltage required, if you have a voltage from a battery, more volts are required to get over these two resistors than these two. And so that comes to now, because more voltage is your current, your I, which is directly proportional to V over R, right? Well, here, notice that our resistance is less here, right? It's 1/2 an ohm instead of these two combined. But your current is still the same going across. Like if I was to treat these two 1 ohm parallel resistors as one.
Oh, it would still be the same across the whole circuit.
Yeah, notice. So there's still the same amount of current going through these, but what happens is the resistance is lower, so your voltage has to be lower as well. For this specific one here, your voltage here, this one, is lower than the voltage across this one.
Oh, okay.
Because you don't need as much, because I said voltage is the thing that pushes your current. And so if you have less resistance, you don't need as much voltage, because your battery has a set amount of voltage that it uses to kind of get across. So say this is a 12-volt battery. Well, it's going to use more volts on these two than it's going to use on the parallel. Okay. And so this equation does ring true, but it's very important to work out your resistance first, and then you can work out your voltage. Okay. So what I would do in a question like this, if I get given that this is a 12-volt battery, and this is a 1 ohm, 1 ohm, 1 ohm, 1 ohm resistor, first what I do is I work out my total resistance, which would be a half for this pink one, and then 1 and 1 is 2. My resistance would be 2.5. And then I could get my current, right? So current, I, is equal to 12 over 2.5, which is 4.8, I think. What is it? Is it 4.8? Yeah, I'm pretty sure it's 4.8. So now that I've got my current, what happens? Well, this current here would be 2.4 because it splits. And this current here would be 4.8. and 4.8. But notice now, if I worked out my voltage, my V is equal to I times R. So my current here, my voltage here, remember we treat these two resistors as 1/2 ohm resistor. Well, if my current's 2.4, my resistance is my current's 2.4 and my resistance, sorry, my current is 4.8. See, it'll be on each one, right? So if I do current here at 4.8 and 1/2 an ohm, my volts is 2.4 volts, right?
All right.
So here I've got a 2.4 volts. So if I was to combine this, well, that makes sense, right? Because it's, there we go. So my voltmeter reading here would be 2.4, regardless of if I measured it over this one or this one. Okay, because my voltage, and even if it was a 1 ohm resistor and a 2 ohm resistor, my voltage across those two parallel resistors is the same. And then here, well, what's 1 times 4.8? 4.8, right? And 4.8. 4.8 plus 4.8, 9.6 plus 4, 10 plus 2, 12 volts. So you notice that my voltage there is, it's higher over the
series part.
Yes, exactly. It has to be, because as I say, the voltage is the thing that pushes the current. That's how I like to think of it.
So it doesn't split.
The voltage doesn't split. No, good. Yes, exactly. I want to show you one more thing. I'm going to rewind all of this. Okay, because you've got all this down. So let me just save this and go backwards. I can reverse. Show you one more thing that William Smith, the TV guy that got me through matric, showed me. And it was just about what volts do, just about volts. You just said, if you ever confused in an exam, just remember that when your voltage comes out of a battery, your voltage is the thing that gets used up in the circuit. And by the time you get back, it then has to replenish. So it's the thing that pushes the electrons, and so it gets used up. And so my green is now different voltage to the one on the other side. And he says, what you do is you must always go, you use your voltage and kind of touch each resistor that you can sort of get to. So it comes out and out. And then when you can't get any further, then you must now do a new one. And what he said is, okay, so notice how you've got the yellow kind of is the circuit is all part of that side on this side, and then you've got red. And so each time you get to a new resistor or a new set of resistors, you now change. But the key thing was that it was yellow there, green there, green there. And what he said was, doesn't matter then what the resistance is. If you get a voltmeter and you connect it there and there, you must know that those voltages are the same, regardless. This can be 10 ohms and this can be 1 ohm. It doesn't matter. The voltage is the same. And so voltmeters connecting the same colors will have the same reading. That was kind of the takeaway. And so that's important. So voltage with the same colors have the same reading. And so he would extend this. He could extend this to more. You could have another one. You could have this here. Okay, but it doesn't matter because they still have separated by the kind of the set of resistors. Okay, so the yellow all connected to the same set of resistors. And so the voltmeter readings will always be the same connecting green to yellow, regardless of the size of these resistors. Okay. All right. I didn't really talk too much about current because I think you get that. The current splits in parallel, but the voltage doesn't, right? So let's just make a big thing here. Voltage. Okay. So this is what voltage does. And whereas the current could be different on each one of these little resistors, could be different. And the size of the resistor will determine how much the current splits. So because the voltage is the same on all three of those, because the resistors might be different, you know that the current has to be different because the voltage won't be. Does that make sense?
Right. Yeah, it does make sense.
Okay, awesome. Okay, so all the best, and I will see you on Sunday.
Yeah. Thank you.
You're welcome, man. So it was more of a lesson than a touch session. But next time, if you want to bring questions, I'm happy to answer them.
All right. Thank you.
Cool. You're welcome.
Okay. Bye.
Bye.